go ahead and get started.
All right.
All right, I will introduce you and I'll give you a 2-minute warning at the 23-minute mark.
Okay, sounds good.
All right, thank you all for coming today. It's my pleasure to introduce Andrew Perry from Springfield College. He is presenting difficult choices in planning to teach introductory differential equations.
Thanks, Gavin. And I want to thank Simeode for accepting this presentation, and thank you all for being in attendance. So this class is about difficult choices in planning to teach introductory differential equations. In fact, these are some of the, somewhat difficult choices that any math instructor or maybe any college instructor really has. You have to make some choices in how your course is going to be planned. But I think that the choices are particularly difficult in differential equations because there's such a wide gulf between the possibility of teaching a course in a more traditional method versus using all the technology that we have today. And also there's a dichotomy between being more theoretical and more modeling oriented. So I will tell you something about how this choice is going at Springfield College, what we've typically done, and what we're thinking about doing, in the hopes that this kind of presentation will be useful to other instructors or anyone else who's interested in differential equations classes. So the Springfield College differential equations class has been about the same as it was when I started teaching at Springfield College. That was in 1999. We have a large population of prospective teachers who are math majors who take this class. So this is generally a gentle introduction for future teachers, typically high school teachers or middle school teachers, who are not generally going to be doing really advanced math or teaching differential equations themselves, but they certainly want to get a good, strong math background for their own teaching, as well as some of our math majors don't major in education, and they're interested in a more strong and robust class. This is a pretty traditional class, and we've always used technology from time to time, but it's not very technologically based. It's been working pretty well for us, but we are always facing the question of, should we change it around? Should we modernize it? Can we do better? And I wanted to give this presentation because possibly other instructors have faced a similar conundrum. And let me describe to a large extent what the character of our normal course. The course serves as a general introduction to the fundamental concepts of elementary differential equations. Students learn the basic theory behind ordinary differential equations and explore simple techniques for solving them. Emphasis is placed on developing mathematical intuition and problem-solving skills in a mostly, not entirely, but a mostly technology-free environment. So our prerequisite is a basic understanding of differential and integral calculus. We require calculus 1 and 2, and there's a small error in this slide here. Calculus 3 is preferred. Generally, of course, as it is with most math classes, the more math you have, the better you can understand the class, but we will accept people into differential equations with just calculus 1 and 2. And at Springfield College, it so happens that these are only 3-credit classes. So they may come into this class with only 6 credits of calculus, and this class actually, in a sense, is developing their calculus skills. So one textbook that's been used is Elementary Differential Equations by Rainville and Bedient, but other instructors have used different choices as well. So we start out by discussing the general definition of a differential equation, classification of differential equations, ordinary versus partial, and of course, different orders. Understanding the order of a differential equation and basic terminology and notation. When is a function a solution of the differential equation? And we move on to first order differential equations, certainly looking at separable equations at first, and then moving on to linear equations and exact equations, all of which can be solved by traditional pencil and paper methods, and then some simple applications to real world problems. Then we look at linear second order differential equations, homogeneous equations with constant coefficients, and method of undetermined coefficients. And we'll look at higher order differential equations, general theory of nth order differential equations, homogeneous equations with constant coefficients, and introduction to characteristic equations. And these 4 basic units are the fundamentals of the course, and then depending on how things go, we will certainly go further. We'll discuss Fourier transforms and other techniques as time permits. Some instructors go a little bit more into modeling, but those 4 units are really the meat and potatoes of the course. So even though this course is not so modeling based, and using pure theoretical math, we can solve a lot of interesting applications. And to sort of characterize the course, I wanted to go through a possible application that we might cover in the course, a logistic equation. We start with the model du p dt equals rp times 1 minus p over k. And then we can solve this at first by dividing both sides by p times 1 minus p over k. And then continuing on, we will integrate both sides, and we'll rewrite the left-hand side using partial fractions. Rewrite it purely algebraically. And then we integrate both sides and rewrite the logarithms as a single logarithm and exponentiate both sides. And there we have a solution of the logistic equation, all of which is pretty simple and understandable. And yet this is a realistic population growth model that might be used. So that characterizes the course as it is. Next, I want to address the question of should Springfield College change to a more modeling and technology intensive course? And I will say that teaching a differential equations course with an emphasis on modeling can be very beneficial for a lot of reasons. And sort of playing devil's advocate against the current course, I've listed a lot of reasons that a more modeling and technology intensive course might make sense. Reason number 1, real world relevance. Differential equations are fundamental in modeling various phenomena across science, engineering, economics, and more. Teaching with a focus on modeling may allow students to see the practical applications of the mathematical concepts they're learning. And reason number 2, interdisciplinary understanding. Modeling with differential equations bridges the gap between mathematics and other disciplines. Students gain insight into how mathematical tools can be used to understand and solve problems in diverse fields, fostering interdisciplinary thinking. Reason number 3, critical thinking skills. Modeling requires students to analyze complex systems, identify relevant variables, and formulate mathematical descriptions. This process encourages critical thinking and problem-solving skills, which are valuable beyond mathematics. Reason number 4, creativity and innovation. Modeling often involves simplifying real-world scenarios to create tractable mathematical representations. Encouraging students to engage in this process fosters creativity and innovation as they explore different approaches to representing and solving problems. Reason number 5, preparation for research and industry. Many careers in STEM fields involve modeling and solving differential equations. Teaching with a modeling emphasis may equip students with skills and knowledge that are directly applicable in research and industry and academia. Reason number 6, connection to modern technology. Advances in computational tools have made it easier to solve and simulate differential equations. Teaching modeling with differential equations can include exposure to computational methods, preparing students to leverage modern technology in their future work. 7th, long-term understanding. By focusing on models, students may develop a deeper understanding of the underlying principles behind differential equations, and that may help them retain knowledge and apply it effectively in future studies and careers. 8th, and second to last on the list, engagement and motivation. Modeling presents students with tangible, real-world problems, which increase engagement and motivation. Seeing the practical relevance of the material can inspire students to delve deeper into the subject and pursue further studies in mathematics or related fields. And finally on my list is reason number 9, preparation for advanced study. Differential equations with modeling serves as a foundation for more advanced classes in applied mathematics, engineering, physics, and other fields. By teaching modeling early on, students are better prepared for advanced studies that build upon these concepts. So moving on to a more modeling-based course could actually make for a more challenging course for us. This could be a little bit a little bit of a difficulty for some of our students who simply want to be teachers and may have difficulty with a more intense class. And I thought about this and I thought, well, if we really want a model for what would be a real aspirational course, why not look at the leader in science and technology, MIT? So I went on to the MIT website just for fun. We can't really emulate MIT, but I wanted to check what their courses look like, with the idea that you can shoot for the moon, even if you miss, you'll land among the stars. As I said, Springfield College can't realistically plan to emulate MIT's curriculum, but it's interesting to look. So let's see what they do offer. So their basic differential equations class is 18.03, study of differential equations, including modeling physical systems of first order ODEs by analytical, graphical, and numerical methods, linear ODEs with constant coefficients, complex numbers and exponentials, inhomogeneous equations, polynomial, sinusoidal, and exponential inputs, oscillations, damping, resonance, Fourier series, matrices, eigenvalues, eigenvectors, diagonalization, first-order linear systems, normal modes, matrix exponentials, variation of parameters, heat equation, wave equation, nonlinear autonomous systems, critical point analysis, phase plane diagrams. Wow. That's a pretty intense course, and I think this is just a single semester. And then there's 18.032, which is much the same, but more emphasis on theory, with more results being proven. So probably even harder. So this would be a pretty amazing differential equations class. And just for the heck of it, let's look at some of the other classes. They have an introduction to PDEs, introduces the 3 main types of partial differential equations: diffusions, elliptic, and hyperbolic, introduces mathematical tools, real-world examples and applications, such as the Black-Scholes equation, the European options problem, water waves, scalar conservation laws, first-order equations, and traffic problems. They also have a class in linear partial differential equations analysis and numerics, which provides students with the basic analytical and computational tools of linear partial differential equations, PDEs, for practical applications in science and engineering, including heat diffusion, wave, and Poisson equations. Analytics emphasize the viewpoint of linear algebra and the analogy with finite matrix problems. Studies operator adjoints and eigenproblems, series solutions, Green's functions, separation of variables. Numerics focuses on finite difference and finite element techniques to reduce PDEs to matrix problems, including stability and convergence analysis and explicit time stepping. Some programming was required for their homework in their final project. And then the last course I have that I found in their undergraduate curriculum was Advanced Partial Differential Equations with Applications. So this includes concepts and techniques for partial differential equations, especially nonlinear, diffusion, dispersion, and other phenomena, initial and boundary value problems, normal mode analysis, Green's functions and transforms, conservation laws, kinematic waves, hyperbolic equations, characteristic shocks, simple waves, geometrical optics, caustics, free boundary problems, dimensional analysis, singular perturbation, boundary layers, homogenization, variational methods, solitons, applications for fluid dynamics, material science, optics, tropic flow, etc. Wow. Well, that's pretty interesting to see what MIT does. And that brings us to the questions part of this talk. Thank you for attending this presentation. This is all I have to say. Thanks for attending Difficult Choices and planning to teach Introductory Differential Equations. And I want to open it up to any questions anyone may have.
May I ask one question?
Of course.
Thank you. In teaching even simple linear ODEs, we usually formulate a problem as finding a function y equals f of x that solves this equation. But as a matter of fact, eventually, in most cases, we get some expression f of xy equals to 0. How do you make connection between these two? I have sometimes I have problems with this.
Oh, so you mean like sometimes the solutions we may find are implicit?
Yes. And after that, say I personally begin conversation that this is a local function. This function has not only a domain, but it has only also range. And if two functions have the same domain, same formula, but different range, the different functions, so forth. I would like to ask you, did you face such problems? Maybe.
Well, definitely the students can find it confusing when there's no explicit solution, right? But I guess there's nothing much we can do except to tell the students that sometimes the only solution we can find are implicit.
Well, I saw that. Excuse me.
Go ahead.
Your requirements for prerequisites are very low, just calculus 1, sometimes calculus 2. And how do you explain them? Say, I will try to say, how do you go from, say, x squared plus y squared equals, say, to 4? How do you explain them what you want to find? Y equals, say, square root 4 minus x squared.
Oh, I see. So about the prerequisites, the calculus 1 and 2 are both required. And it's calculus 3 that's preferred, but still it's only 6 credits.
Mm-hmm.
And yeah, I suppose if the solution is x squared plus y squared equals 4, then there's the two branches, square root of 4 minus x squared and the negative square root of 4 minus x squared. So I guess I would explain that that relation has two different branches.
For sure.
And even though the students are used to explicit functions, still our computations may show still an implicit answer.
Thank you. I will think about it. Thanks. Thank you very much.
Thank you for the question. Oh, Tom, you have a question?
Yeah, question and a
Okay.
couple of comments. Does your course cover systems?
It can cover systems. There's those basic 4 units, and some instructors, so we're allowed to go as far as we or feel like we're able to with the students. And yes, I mean, I think we've used systems are wonderful in modeling in basic modeling.
Well,
So we
in
usually cover systems, I believe.
real life applications and in the real world, much is done with systems. Um,
Absolutely.
the second thing is, I would probably not be looking at the MIT course. You might want to look at the BU course. Blanchard, Devaney, and Hall have written a wonderful textbook. And the MIT course, even the basic one, I doubt that they can cover all of that in a semester. And I'll tell you where I'm coming from. For 5 years, I taught the Ordinary Differential Equations course in the math department at Harvard. And there is no way I could get through all of that stuff. Okay. And I would have to leave out an incredible amount to do anything in any sort of depth. And I can't believe that my students were they could sit through an MIT course just fine.
It's pretty crazy. Yeah, we can't aspire to the MIT class.
Well, I'm not even sure MIT can aspire to the MIT
Maybe not.
class.
Maybe not. I've never. I went to Williams, which was a pretty strong academic school for sure. But I think MIT is at a whole different level. But I don't know if they can live up to their syllabi. And I believe you if you would say that that's really aspirational for them too. Oh, let's see. I see. Cesar, you have a question.
Yes. Well, first of all, thank you, Tom, for that comment. That's very enlightening. I work for a branch campus of a land grant institution we will not mention, Penn State, and the way that the courses are orchestrated is fundamentally flawed. I mean, I learned differential equations under V. Lakshmikantham, so I come from a very robust understanding, and the basic ordinary differential equations course at Penn State is actually 3 credits, and there's a 4-credit version that includes partial differential equations. And again, it's very similar to what they portray at MIT. But like multivariable calculus is not required. And so I find myself teaching students what partial derivatives are, because I don't see how you can explain what exact equations are, for example, without partial differentiation. I mean, the proof demands partial derivatives. But also something that I've been struggling with, as I've been moving along in my career, is that beyond the modeling, I mean, we need to accept that these things exist, right? Computers exist, cell phones exist. And I have struggled with some of my colleagues who would think that a difficult problem is one that requires integration by parts 4 times. Whereas nowadays, I've actually added an additional hour to all my differential equations classes, and I take the students to a computer lab, and we use Mathematica just to work with nonlinear equations and just expand on the topic, because my dissertation advisor, he used to comment, differential equations is taught in a cookbook fashion. If a question looks like this, you do this. If a question looks like that, you do that. But the moment that the equation does not look like the model, then the methodology is very, very complicated and well beyond the undergrad. So
Right.
so I struggle, would like to put more modeling, but I'm beholden to a big system that has requirements that have to be covered, and yet I still manage to squeeze in things like just adding a computer lab to the entire course. But it's complicated, right? Teaching modern differential equations is a very complicated affair. You know, coming from the notion that most differential equations are unsolvable. You know, so I agree with Tom that we should have more systems and less, you know, less dependence on, you know, little algebraic methods like on determinant coefficients, right? I cover it and then I explain, you know, this method is good for simple equations, and then you move on. You use variation parameters because you can express your solutions as integrals. You know, we spend a lot of time just working with algebra where those operations could be relegated to technology and we could focus on the bigger ideas.
I agree, Cesar. I mean, that makes some sense. I'm afraid to make changes that are too radical, in part because I see so many students coming into my basic college algebra classes and they have no intuition because they've been corrupted by calculators. So they have no intuition for arithmetic. Taking away too much of the pencil and paper work, I'm a little bit worried that the students might lose intuition for pencil and paper calculus as well. But you're absolutely right. The using technology has a lot of advantages. Tom.
Yes. How big are your classes?
They're amazingly small, actually. So we've had trouble in recent years getting enough math majors. I mean, we used to maybe get 10 or 15 in differential equations classes or even 20, but now our classes are usually 5 to 10 is all.
So one thing that I've tried that seems to work very well and to wean them off calculators is have them work in small groups, but send them to the board to work in groups. They seem to work better. They seem to use the calculator less, and it's easy to rove around between groups and give hints and see what your students are doing. Also, if a student, one group comes up with a really good solution, you can call everybody over to that board and you can have them present their solution.
And so your comment refers to any kind of class, correct? Not just differential equations.
I've done it mostly in differential equations. I haven't taught calculus that much recently, but you know, it works. It seemed to work very well with differential equations.
Interesting. Nice idea. Thanks.
I have a question for you, Andrew. Do you use any sorts of graphical software or, you know, any solvers in class to show solutions of equations and stuff like that?
So we introduce, so when I've taught it most recently, I've used Wolfram Alpha.
Okay, all right. Right, because I think that's how you create a lot of intuition, right? You know, showing direction fields, showing the solution, the curves themselves. So something that I capitalize a lot on now that you present the logistics equation is, you know, when I talk about nonlinear separable equations, of course, including the logistics equation, I look at real world data from the COVID years, and it is incredible. I mean, how you can actually see the S curve at the different outbursts throughout the data for, you know, for different countries. And that has a really strong impact, right? You say, you know, so the logistics equation, you know, it's a nice, cute little model. It's not necessarily incredibly realistic. And yet you look at the actual data and then you see the patterns. And so I rely a lot on just visual intuition so that at the end of the day, you know, the solution can be left in a more theoretical manner, but of course, I'm working with engineering students, which is different than your, you know, than your cohort of students.
Cesar, that sounds fascinating to use the real COVID data. Can I ask what's the source of your data?
Well, after unfortunately, what was the university in Baltimore that closed? They had an incredible website. I forgot right now. Please remind me.
Johns Hopkins.
Thank you. Johns Hopkins had an incredible dashboard and they closed it. I just got to regular browsers and look for just COVID data, and they still cover it pretty much. I mean, you can still find dashboards with lots of entries for, death rates, infection rates, overpopulation, and so on. And you can select different countries.
Nice. Oh, I'll definitely check that out. That sounds really useful. Are there any other questions or comments?
Yeah, I put my question in, sorry, let me set my screen. Okay.
In
The chat box.
the chat.
Yes.
Okay, let's see.
Yes,
Uh,
in the chat. Yeah, I put in the chat. Yeah.
Why am I having? I'm having trouble.
Okay, let me read it for you. So, did you use automatic reading software like WebAssign, MyMathLab, Workbook, or MyOneMath?
Oh, now I see the chat here. Yes, automatically. In the differential equations class, I never have used that. I've used my open math a good amount in other math classes. What about yourself? Do you use those systems?
Yeah, I'm using my OpenMath, and recently I use a WebAssign.
I really do like my open math for being free, and it's
Yes.
pretty good despite being free. Any other questions or comments or thoughts of any sort? Well, in that case, thanks again for everyone for attending and staying on till the end. And I guess we can close off this section and move on to the next, the 8 o'clock sessions.
Thank you, Andrew.
Thanks, Cesar and Tom and Widodo, for your nice questions.